Assalamualaikum students. So let's resume back our lecture to Rankine vapor cycle topic. So previous class I've given you the video on Carnot cycle and also Rankine cycle. So I just want to recap back the theory and emphasize on the theory on the Rankine vapor cycle. So you have learned that there are some issue with the Carnot vapor cycle, and we can eliminate the impracticalities with the Carnot cycle by superheating the steam in the boiler and condense it completely to the condenser. So the issue can be solved with the simple ideal Rankine cycle. So the process start with pump, okay, where you have a saturated liquid enters the pump and is compressed isentropically to the operating pressure of the boiler. So here your water temperature increase somewhat during this process due to a slight decrease in specific volume of water. So process 2 to 3, so your compressed water will enter the boiler as a compressed liquid and leaves as a superheated vapor, steam. At the state 3, your boiler will get heat, okay, Q in from the furnace or nuclear reactor. Okay, and then from process 3, your superheated vapor will enter the steam, the turbine, where it expands isentropically. So you have two equipment that involve isentropic process. Okay, so S1 equal to S2 and your S3 is equal to S4. Okay, your turbine will produce work by rotating the shaft connected to an electric generator. The P pressure and temperature of the steam, okay, from process 3 will drop during this process to the value at state 4. At state 4, you will have a saturated liquid vapor mixture with a very high quality, okay, more than 90% or 80. Okay, then at state 4, the saturated liquid vapor mixture will condense at constant pressure in the condenser and leaves the condenser as saturated liquid, and the cycle will repeat again. Okay, so on your right side here you have a TS diagram. So if the area, okay, from A to 3B, that is your heat transfer to the water in the boiler, okay, your QH. And from process A14B, that is the heat rejected by the condenser, is Q out, okay. And the middle one here, the area under the red curve, okay, area enclosed by the cycle curve. So that is your net work produced during the cycle, or sometimes we also call it power. So your net work is equal to work of the turbine minus work of the pump, or Q in minus Q out. Okay, in the next slides, these are all the formulas related with each state. Okay? And the final, usually the question will ask you to calculate the net work net and also the thermal efficiency, ideal Rankine cycle efficiency. There's two ways to calculate. For Rankine cycle efficiency, you can calculate by using W net over Q in, or 1 minus Q out over Q in. You will get the same answer from these two equations. So let's try apply all these equations in our problem. So here we have example 10.1. Consider a steam power plant operating on a simple ideal Rankine cycle. Steam enters the turbine at 3 MPa and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kPa. determine the thermal efficiency of the cycle, your N, the Rankine cycle efficiency. So we can start with state 1. Okay. So at state 1, we have P1 equal to 75, and okay, from previous slides, so state 1, you have a saturated liquid. So you need to look at your steam table, A5, appendix table A5. So from these two information, you need to get your H1 and V1. So H1 is equal to 384.44 kJ per kg, and your V1 is equal to 0.001037 meter cube per kg. So we need to collect all this information first before we can start doing the calculation. So state 2, okay, P2 equals to 3 MPa. So your pressure increase after the pump. So we can calculate the work of the pump using this formula, V1 P2 minus P1. So your V1 is this, okay, 0.001037. P2 3 MPa, convert it to kilopascal, minus 75 kilopascals, and you need to convert kilopascal to kilojoule. So 1 kilojoule is equal to 1 kPa dot meter cube. So this can cancel out meter cube. So you left kilojoule per kg. So plug in this in your calculator. So your pump work is 3.03 kilojoule per kg. Then at state 3, so your pressure, the information here, it gives us the condition at state 3 because it's steam enters the turbine. So P is 3 MPa, your temperature is 350 degrees Celsius. So this is at superheated vapor. So you have to look at table A6. So from there you get the values of H3 and S3. So these are the values. So next, state 4. State 4, your pressure is 75 kPa, and you will be at the saturated liquid vapor mixture. But keep in mind that your S3 is equal to S4, and you need to calculate for the quality because it is a mixture, so you need to calculate for the quality. So you need to find SF and SFG from steam table A5 at 75 kPa. Okay, then you use this formula to calculate for the quality of liquid vapor mixture. So here, plug in your SF and SFG values, and your S4 is equal to S3. So take this value as S4, then plug in your calculator. You will get at quality of 0.8861. So with this new information, you can calculate for your H4, enthalpy at state 4. Okay, so HF plus X4 HFG. So get the value of HF and HFG from table A5. Okay, these are the values. Okay, and you will get H4 as 2403 kilojoule per kg. Okay, so now you already have all the enthalpy at each state 1, 2, 3, and 4. So with that information, you can calculate for Q in and Q out. So these are the formula for Q in, and the bottom one here, Q out, is H4 minus H1. So you can calculate for Q in and Q out by plugging all the enthalpy that you have calculated before this. Okay, and with that information, you can calculate for and the efficiency, thermal efficiency, where 1 equal to Q out over Q in. So just plug in your values. Q out 2018.6 divided by 2728.6, then 1 minus that ratio, so you will get 0.26 or 26%. So your thermal efficiency is 26%. So this is one method to calculate for thermal efficiency. Okay, The question asks for thermal efficiency. The other way is by calculating the W net. So W net is equal to W turbine minus W pump. So W turbine, the formula is equal to H3 minus H4. So similarly, you just plug in the values that you have obtained from previous steps to calculate for work of the turbine. So your new N is equal to W net over Q in. So your W net, okay, once you got your turbine, you minus with your W pump. So that is your W pump is 3.03, okay, here. So you will get your W net as 710.1 kilojoule per kg. Then divide by your Q in. So with these two values, you will get the same answer, okay, 0.26 or 26% as your thermal efficiency. So that's all for this. I will continue with another example.